Fact 2. The motion of a falling object. The purpose of this experiment is to capture an object's motion that is dropped from rest, then create two computational models, one that only includes the effect of gravity and the other that includes both the effect of gravity and drag. In the end, we will find that the graph including gravitational force and drag force more accurately predict the position of the chip bag. We'll talk about several fundamental principles, including Newton's second law, the position update formula, gravitational force, drag force, and net force. From Newton's second law, we can find that delta P equals F net delta T, where the final momentum minus the initial momentum equals F net delta T. We can break up momentum to be mv, divide by m, and we can get our velocity update formula shown here. Gravitational force is equal to negative mg j hat, where m is the mass of the object and g is 9.8 meters per second, which is gravity on Earth. The drag force is equal to the drag constant times the velocity squared, v hat. Then our F net is going to be the gravitational force plus the force of drag. Our system consists of a crumpled empty chip bag, and the surroundings includes everything else. Our initial conditions had position at 0, negative 0.01710.763, 0 meters, and velocity was 000 meters per second. Here is the video of our falling object. We use the initial conditions of the experiment to set up our computational model. So we can see here that we have our mass of our object set at 0.005 kilograms or 5 grams, the initial position and initial velocity shown here. The time starts at 0.2 and delta t is 0.033. J hat is a unit vector pointing up, so that's why it's 0, 1, 0. And we found that our B was 0.02. Okay. So here's our calculation loop. We find the weight force, or force of gravity, which is negative mg j hat, and the force of drag, which is negative b times the magnitude of velocity squared times the v hat, which is shown here. And then F net is our weight force plus the drag force. Then here we apply the momentum principle to update the ball's velocity and position. And then we iterate time. This graph shows the observed model versus the drag model versus the no drag model position. You can see that the no drag predicted a much further distance traveled than the drag and observed model. You can see that the drag and observed model are actually very close, which is why we know that the drag model is a more accurate representation of the real world. So what if the object was actually initially thrown downwards? How would that affect the terminal velocity? And which model, the one including the drag force or the one including only gravity, predicts an accurate terminal velocity? Well, the thrown object experiences a greater terminal velocity than the object that is dropped because it is thrown with an initial velocity. We compared that in the graph right here. Terminal velocity occurs when the force of drag pointing up has exactly balanced the force of gravity pointing down. This means that at terminal velocity, F net equals 0. Therefore, the model that can predict terminal velocity is the one that includes both gravity and drag, because as time reaches infinity, F net becomes 0. And when F net becomes 0, velocity won't change, which means it is at terminal velocity, seen here.